No, no, no. Yes, sir. Thank you.
Okay.
Yeah, maybe I spent too much time in the the first page, but this is outline of my talk, and there's three components. First is introduction to the HPC, and the second one is the examples, and the third one is letting you know how to use the HPC, how to connect. So let's move on to the first. Which is before starting to explain the HPC. So I'd like to mention my personal experience regarding HPC. Um, so when I first started my PhD project, I was so excited. The project was about the image, compression and reconstruction problem that can be applied to satellite imageries or the MRI, medical image reconstruction. Briefly, it changed the way image is taken and processed. Traditionally, it is stored first in the memory and then compressed, but this technology can do image acquisition and compression at the same time. And then, the reconstruct it at the decoder side. So at the time, we were able to develop a method which is around 30 times faster than the state of the art method at the time. So while developing the method, we needed to test a handful of algorithm parameters to see how those affect the quality of the reconstructed images and videos. At the time, I didn't know anything about the HPC. I came up with a naive solution. In the middle of evening of the computer lab, as you can see in the MSU library, and I sit on one computer and open the program, MATLAB, run a calculation, and move to another computer, do the same, and then again and again for all the calculation that I need. And I was able to get all the results by the time um, the before closing the library. But I've got an email that from the administrator that I cannot monopolize the all the resources. So yeah, so that's my fun experience. But I asked my advisor whether there's another way I can deal with this problem, and he let me know the existence of HPC installed in the EC department in MSU. So that's how I started working on that. So another reason you need to ask your advisor if you need help. So let's get started. What are we first need to define the terminology that commonly used in the HPC community. So here are two different systems are shown in the screen. The first one is a workstation, and the second one is a computing clusters. So both the system is in some aspects is similar in a way that the computer can connect, should connect the server or workstation, whether it's a workstation or computing clusters. You do some works through the network, and then you get the results after the simulations. So and also the both of the systems are shared resource. So you run the program, but you may expect other users can run the simulation as well. So the in workstations, it just run just like your desktop. So if many users access to the workstation and run the program, it may delay or lag your entire program. Just like you have a multiple program on your desktop would slow entire system down. So that's what would happen in the workstation. And also, at the same time, it may be not running entirely running on the workstation. So it could be a waste of time, sitting there not running a simulation. On the other hand, the computing clusters uses you know, some technology called job scheduler or load balancing to efficiently manage the resource. So job scheduler is, assigning the computing resources to each task so that it runs in order that it receives. Is sometimes the priority or the order it receives or the number of jobs running in the queue, waiting in the queue, or running in the computing clusters. That's the factors that based on which it decides. And the load balancing is it organize the entire system so that it's smaller jobs in the smaller nodes and then larger jobs in the larger nodes. So, so that it does not have a waste of resources. All right. So next slide, we're going to see the brief history of the HPC. So on the center, we see that on the chart where it describes the computing power and physical size by year. So as you can see, the first one is ENIAC, which was developed in the Penn State University in 1946. The name is represent electric numerical integrator and computer, which was first used for the World War II era to calculate the projectile of a ballistic. So it is basically solving the differential equation. And at the time, the skilled person would take 20 hours to solve all the calculation, but it can be able to solve in 30 seconds. So which is quite a advancement at the time. But the first successfully commercially available supercomputers recognized being the CDC 6600, which runs in 10 megahertz. As a comparison, the usual computer nowadays runs in 3 gigabytes or 3 gigahertz, so which is quite slow, but it is faster than other machines at the time. And also you notice that the size of the computer, so which takes about the room size compared to the house size of the ENIAC, 1800 square feet is quite large to accommodate in research facility. So this computer is sold over 100 machines over all the national labs in the country at the time. So which is quite successful. Since then, there's many competitions occurred during the worldwide to make a faster and the larger computers. Fast forward to the 2013 and 2016. In those days, U.S. is leading those competitions. Only the place 2002, NEC is a Japan cluster, but 2013, 2016, Chinese supercomputer beat the U.S. computers. How about now? So can you guess what is the world's fastest computer as of today? China or Japan or US, back in the US or other countries? The answer is Japan. So Japan is 415 petaflops. The flop is the unit of the measure how fast the computer can calculate. So which is 3 times faster than the US first HPC summit on Oak Ridge National Lab. Another question then, what about the single desktop, where it resides in those years? So your personal computer using i7 computer is in between 1985 to 1997. So through the time machine, if you bring your laptop to one of these areas, your computer will be the world's fastest computer. All right, what about the HPC cluster in MSU? So it has a 5.4 petaflops and ranked at 60 in all worldwide and overall 5th in academia as of 2019. So yeah, so which is quite astounding results. So which is provided by the NOAA, the weather prediction, and this is quite a resource that we have. All right, so let's move on to the anatomy of HPC. What is it composed of? So the CPU is a main building block of this system, which usually have two processors, each of which has 4 to 10 cores in a chip. So that is integrated in the computer card. Usually two chips are built in, and then the multiple cards are also integrated in one node board. So this is what we commonly called a node. And then that boards are also stacked in the cabinet with some accessories like network cable, optical fiber between the nodes, and also cooling system is built in. So those cabinets are combined together, and that's what we call a cluster. So yeah, we're going to introduce what cluster system we have in HPC in the coming slide, but this is what we have. I'd like to note something here. So we have been using the CPU traditionally as a main component of the node, but as the quickly advances we are of the GPUs, we can integrate one or two or multiple GPUs to node board. So then, it can communicate each other to get some faster calculation results. So on the top corner, it it shows a difference between the CPU and GPU, where you can see the CPU has a few um, the very fast computing cores integrated, while the GPU has uh, a lot of much more uh, less computer capability. Those are integrated together. So um, originally the GPU is used to process the graphic components. So you can do to show some visualization results. It uses a GPU, but nowadays in the machine learning is advanced, and the deep learning neural network is emerged, widely used. So this processor GPU can handle the matrix operation very efficiently, the multiplication addition. So it started to use that purpose in research and real life of application. So nowadays it's common to see this hybrid system in the HPC. All right. So let's move on to the available resources in the MSU, the HPC cluster. So three of the computer clusters are available. One called Shadow, one called Scout, and one called Orion. So each of the clusters have their own number of nodes, available nodes. Um, because Orion is most recently added, so naturally we can think Orion is fastest. So then the Shadow is the next, and Scout is slowest that we have. But the Scout is the only cluster that has the GPU. So if you have some jobs to run, GPU jobs, then the Scout is the way to go. And we have a Titan server, which is only for the storage, and also there's workstations, Viking 1, 2, 3, so you can use other resources. And these are the available softwares. You can do some programming. You can do use a math software and a computer engineering and machine learning. So those are the specifically available. Some commercial softwares are also installed, so you can, if you get the chance, you can use all those softwares as well. Okay. So now let's move on to the HPC examples that our research facility have done in the past. So first is the molecular dynamics simulation coupled with the finite element method. And then the second one is the machine learning example, supervised learning. But I'm going to show you how to um, optimize the hyperparameters that we have. So the first example we're seeing on the screen, which is called the SGB map. So which should basically show the different materials on the chart, shows us a strength versus the mass. So if you looking at the polymers which is in the center, which is reasonably lightweight, but shows a reasonable strength. And then if you go to right-hand side, it's a very strength but heavy materials, which is metal and metal composite, metal alloys. So many research has done to pushing this, line, as you can see, two constants line pushing towards the upper left corner so that, we can make a lightweight but strong material. So, as an example, polyethylene is a very versatile material. It can be used for the pipe, construction helmets and loops, and military application, which is a bulletproof vest. Um, yeah, so the question that we have for this material is what is the damage mechanism and how it affects the strength of the material? So starting from this science question, we can go further to develop the engineering, better engineering material, better composite. So we have to address this answer first before engineering question. So the polyethylene, for example, the nano phenomena is shown in the box. So it's a zoom in picture of a nanoscale, and then zoom in another zoom in, which is the 20 nanometer. And then finally, the chain polyethylene monomer chain is shown in the middle, which is the one less than 1 nanometer. So the feature that we have is a chain entanglement, which is the chains are twisted together. If you can see on this, this video. So this is two chain. If you twist, it does not move, as it normally move. It blocks the other chains. So that's the chain entanglement. The chain slippage is just if you pull it, it's gonna, pull it this way through the slippage process. Or, it bounce breaks in between these chains. That's another example. So we have to address this, complex mechanism in the nanoscale to better predict in the continuum level. So that's what we have done in the past. We run several different molecular dynamic simulation. One of the examples is a tension test. So as you can see in the green bubble, which is the void, it is nucleated at certain frequency. It grows in certain time rate, and then it merges together at a certain rate. So we can get those microstructure, nanoscale information, and put it into a single equation. That's the damage evolution equation that we developed. Not only the tension test, we do the compression and a shear test, and then because of the random nature of this simulation, we run multiple of the different configuration, 9 different configurations. So which is worth of 6 months of the computational calculation. But based on this, we transfer the knowledge to the final element method, and then we get um, the improved results compared to the existing method, the model. So as you can see, the blue dashed line is our results coming from the molecular dynamics simulation. So which is quite accurate than the other model. So this is what we have seen in the past. So using HPC, you can run 100 times faster than the personal computer. So that's the beauty of the HPC in this case. So now let's look at how the multi-core works in the MD simulation. So molecular dynamics is the parallelism achieved by the partitioning the simulation cell and assigning a core per each code partition. So as you can see, the computing core is assigned this block, and second core is blocked this way, and etc. And then we just need to have some information from each cores to the center of our simulation, or transferring the other cores, aggregate all those data and get the other necessary information like forces and energies in the presence of other atoms and the boundary. So those are the necessary information that we need. So that can be achieved by the technique called the message passing interface. So it is usually implemented in the software. You don't have to worry about this, under the hood technique, but it uses a multi-core as a naturally when you run the simulation. So because I mean, it, unlike you running the entire simulation using the single core, it needs some communication between the cores. So that increases the burden, excuse me, of the communication burden. So, as you increase the number of cores, it would speed up the simulation, but there's a limit. So the computational burden is increases. So, and at a certain point, it's saturated. So then, even if we increase the number of cores, it will be stay the same. So at that point, from that point, you are wasting the resources. So, which means that there are some procedures that we need to do to find the optimal number of cores for a certain simulation. That's probably what we need to do before running the larger scale simulation. Okay, so next example is the machine learning. So, so one example is shown on the blue box, which is typical deep neural network. A deep neural network procedure is composed of multiple computational layers with some parameters, as you can see, weight and biases, to turn the input variables such as coordinates and time and some simulation into output as a temperature, for example, as closely as possible to the desired target data. The goal here is to find optimal parameters through the learning process. The learning process is typically done through the multiple iterations or training group, updating the parameters by minimizing the loss function, which is in here, and the mathematical notation, which is just basically the mean square error between the prediction and the measurements. So usually this process requires big data. However, including law of physics as a prior knowledge in the training process can achieve the robust prediction results even with the small data. This is called physics-informed neural network. As you can see here, the first part of the equation is the same as the previous one, but we added the governing equation to this total loss function as an additional regularizer. Then we can get a lot better results. For one of the example is shown on the bottom. So regular deep neural network with 1,000 samples of measurements shows this prediction results. So you can see the overlapped blue and red dashed line. So which is a snapshot of the time of this entire simulation, which is a heat equation at the bar. And the other one is the PINN, this technique with the 10 data sample. So as you can see, the error, visual error is the same, very quite similar. Numerical objective number is also the same, which is 1.5%. Okay, within this framework, we needed to find the optimal network, which is shown in here on the top. So network size determines the expressibility of the network, so you can express the complex nature of the problem. But if it expresses too much complexity, then it is a it causes some risk of overfitting. So we would like to find the simplest neural network structure as possible, and also it aids to reduce the computational time. So these are the what we call, I mean, the components of the neural network is what we call the hyperparameters, which is a layer and nodes. So nodes are the, within one layer, which is an interconnect between the previous layer, loading the previous layer and receives and process with nonlinear activation function and transfer it to the next layer. So you can increase the width by increasing the nodes, or you can increase the depth through the changing the number of layers. So to so this is kind of a multi-objective problem because we want to construct a neural network that achieves a good accuracy and that performs a calculation as quickly as possible. Um, to do this, we consider the many factors, including this nodes and layers, uh, but also the different types of optimizer and running rate, or the number of training data, etc. But in this particular case, we only deal with the nodes and layers. So the possible candidate we listed here is a 4, 5, 6, and the possible candidates are 10 through 30. So, and also, this neural network involves randomness, random initialization values per node. So we have to run at least 3 calculations to get the uncertainty. So on the right, we got the results. We actually will run more calculation, but for the sake of space, we only show some of the results here. So, by the way, as you can see, the number of nodes times number of layers, number of layers times number of nodes and number of instances that brings number of total calculation that we need to run. So this is the results. So the left column shows the prediction error, and the right column shows the computational time. So there's some uncertainty bands are represented as a gray color. So through this process, we can decide which point is the best or optimal for this particular problem. We can do certain Bayesian techniques to do that, but this is just for the sake of what we do and what we can do using the high performance computing. So HPC, through this example, we see that HPC enables running independent simulations simultaneously. That's the another aspects of the HPC. All right. So next, we're going to see how to use HPC, especially in MSU. So there are 2 different modes available. So first one is interactive mode, and the second one is unattended batch mode. So the interactive mode is you're connecting from your computer to the development node, which is just like you use a workstation. So you run this calculation on the fly. And you could use, if you want, a graphical user interface like MATLAB or Mathematica, and then run the calculation on the fly. But it is limited to a short time in the cluster, about 30 minutes. And if you, in the middle of calculation, if you close the terminal, then it'll lose a connection at the same time the intermediate results. So that's cons. So because of the reason this development nodes is strictly used for the compiling, debugging, and testing and visualization. So that's the purpose of the so small case study. And on the other hand, the unattended batch mode has a little bit complex structure compared to the interactive mode. So the first, the computer is connecting to the login node, and then if you submit a script, a job script, and then it put it in the system called Slum, and then it decides, you know, which job runs first or next, okay? And how many jobs are run in the capacity, the full capacity of the compute node. And after the simulation, it, store the storage results, the storage, and then you can access login node and to get the result. Usually the results are stored in temporary, so you have to transfer those data to the local machine or the data cluster. All right. The benefit of using this cluster, is longer time and a larger scale. And also, you don't have to sit on your desk to finish your results. It runs by itself and it'll let you know when it finished or there is a problem during running. So, but the problem or cons, one of the cons is the you need to learn how to write the job scripts. That's probably one of the cons, and you need to learn some Unix commands. So that's another things to do. All right. So 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 the to submit the jobs, there's only we can think of that as a 3 steps. The first step is to connect to the login node and then prepare the batch script. The consideration here is software, what software you need to use, and then number of nodes or GPU nodes. Those kind of specification is required. We're going to see in detail in next slides, but I'd like to mention that the software unlike your desktop, you install whenever you use, you just click the software to run. But in the cluster, you have to request a resource. So you have to request what software you need to use. The reason is that, some software has a dependency. So you have to have some sort of the uh, the package of your software. So that depends on the compiler or MPI system. So you have to tie it into those basic setup so that you can run the simulation without a problem. So because one software needs some different libraries, another software needs different version or different type of library. So you have to split that up in each backend. So that's why you need to specify your software need in the script. And then lastly, after the simulation, you have to transfer those data because it is a volatile, or it will be swept, cleaned in frequently. All right, so let's take a look at the first step, which is to connect the cluster for job submission. So which is done through the SSH, which is a secure shell. Typically, you can do SSH in the terminal, SSH, and user ID, in my case, Sungkwang at, this is a cluster name, and hpc.msstate.edu. So this is an example. And then Windows users need a special software like a PuTTY shown here because Windows does not usually offer the secure shell as a default, but Unix Mac users have them as a default, so they can run on basic terminal. So once you run this command, as you can see, maybe here, server, and then you have to enter, dual authentication. process, and then you get the welcome message, so that here's some things you can do, here's something you cannot do. That's basically uh, some some sort of a threatening message, but you have to follow, comply this rule. All right. The second step is to prepare a job script and submit it. First, you need to, basically go to your work directory. Typically, it is inside the work directory and username, and then project name. You can make a project. So, like for example, work Sungkwang, maybe project one is my, or PINN, that's a project name. So you can create a folder under your username and run the calculation. So unlike, there's another directory, home directory. Um, it all the data stays permanently, but the work directory, as I mentioned before, all inactive data can be deleted. So you have to move around after the simulation. So we'll see it in the next slide. And then after going to the work directory, you have to write a job script. You can just transfer the job script, or you can write on the terminal using some writing software, writer software like um, Veeam or Emacs or some other things that you want to use. And for example, the example of the job scripts on the right-hand side, and there's the special program with the shop sign. There's a job name, or this is a queue. Uh, so 48 hours, 400 cores, and then output name, and then the project account. If you don't have a project account, then it runs with the least priority. So you may want to have a project number, uh, and then email address, and when it notify end or fail, and then how long it runs. The maximum wall time is a 48 usually, and then number of nodes and your request and number of tasks, which is the same as the number of cores. So 40 cores, and then this is the software specification module load, Intel MPI module load, the MD software, which is length, and then it runs with the srun command, so which is a software name, and then input, and this is just a software command that you want to run. And then after finishing up this job script, and then save it, and then you can submit it through this command sbatch and the name of the script. You can monitor and then cancel some commands. You can check those commands in this link. So I don't want to, I won't go into too much detail. You can check. Another thing, okay, yeah, we can talk more in the next slide. So the final step is transferring the resulting data. So to initiate the transfer from the remote to local, or between two remote hosts, HSCP can be used. So to copy a directory from the cluster to a project folder for longer storage, you can use this command. SCP is the program name, and then R is a iterative. If you have a soft folders and you want to do this to copy an entire folder. So work, same as a Sungkwang or project name PINN, and then username in the different server. I mentioned that Titan is a server for longer storage. That's what you need to do. And then this is the address, and then the directory in that specific server. This is one way to do that, but you can use some software like a WinSCP for Windows, FileZilla for other system, Linux or the Mac users. So this is a GUI version. You enter the address and your ID and password, and it'll show up on this kind of familiar Explorer window. So this left-hand side shows local, and then the right-hand side is a remote. So you can move files and data, vice versa, in either direction. All right, I think that's it that I prepared. So let me summarize what we have looked at. So the takeaway message is the HPC can accelerate your research by using it. You can tackle a bigger problem in the same amount of time, or you can solve the problems the same size in a much less time. But it requires some new get things that you need to get used to. First one is a Unix system and program commands. For example, cd um, change directory, ls, show directory contents, move the folders or data, and then copy of files or directory, making a directory, or submit a job, and then show the screen the jobs in the queue, or the moving the files to different servers. And one last thing is the job scripting, but the HPC offers online generation tool, so you don't have to too much worry about what you need to do. So it can generate the scripts for each cluster. So if you enter your need, and it'll automatically the contents for the script. You can copy and paste that contents in the file, and then just submit it. All right, that's it for today. Um, Thank you for your attention, and the remaining figure shows the previous achievement by HPC and MSU. You can go to this website to see more in detail. Any questions?
Thank you, Sungkwang, for that presentation. I have one question for you. So what you're saying, so your running code and your batch script or something are different. Do you submit your code within your batch script?
Yes. So this can be your program. So it can be MATLAB, it can be Python.
Okay.
So you just need to put the srun command in front of your software command. And then this is a separate file. And then you put this contents in this, in some form of text, like I name it maybe script.sh for conventional reason, and then sbatch script.sh. Then it'll put in a queue and then waiting list, and then it runs by itself. And then once it's done, you will get an email for the completion.
Okay. And you generated the batch script on the website that you posted at the bottom here?
Exactly. So you can go to this website, and then bottom of the website has a web feature. So you can there's a menu inside the web, and then you can change the number of cores that you need, a number of nodes that you need, and the softwares, and then it'll create this, especially this specification, job specification.
Okay.
So then you don't have to worry about it.
That makes it simple and easy, or easier to use.
Right.
Does anybody else have any more questions?
Yes, I have a question, Christian. So first of all, hi, Dr. Sungkwang. Thank you for your informative presentation. And thank you, Christian, for organizing this webinar. So I have actually two questions, Dr. Sungkwang.
Yes, sir.
The first one is that if anyone who is a student in kind of MS state, so they can use these clusters in HPC. And my second question is that if you want to kind of use a script for which there is no dependency, like maybe in our area, we use, for instance, Groovy Optimizer. So I think maybe most of the people who are using these HPC clusters, they don't need this Groovy. So can we ask the person who is in charge of these clusters to install such dependency on the cluster?
Yes, sir. The answer is yes, but there's some stringency because so through the director's discretionary, the HPC is a cluster that is there has a member center, CAFs, HPC, CSS, and GRI. Through one of those directors, you can request a resource for certain projects for certain period of time or class projects, but it is limited by the the project account. So without this project account number, the all the jobs as tagged as a least priority, which means it runs when there's no job or there's some remaining resources not running, then it'll run those least important or least priority jobs. So that's a kind of a difficulty, but so if you're involved with one of the projects in the HPC cluster, then you can enter this account number and then run normal speed. And for the support, there's a contact point in the HPC. It's not easy as it sounds, but you have to communicate enough for them to install for particular specific software that for your need. So I think it's better to co-op with your colleague. First test, who knows the program well enough, to compile by himself on the cluster and test it. It runs well. You can, give them information to the HPC, then they're willing to set it as a global software for the users can utilize.
I got it. Thank you, Dr. Sungkwang.
And thank you.
So just one question, Dr. Sungkwang. I think it's a very informative presentation, and actually I like, to be honest, the last part probably the most useful for majority of us. So the question is that for when you are setting the directory, are you referring to a local machine for that directory, or you need to actually copy this to the server, your code and program to the server first before actually you need to run the program?
Yes, sir. Yeah, thank you for asking that question. So it is unclear that, I didn't put as a step zero. The step zero is you have to copy all the data if you need. But some cases, the data and programs are usually stored in the project folder. So you just need to copy one of the remote folders to another remote location. So I assume that you already have the program, but if you don't have, you have to copy those all the data and programs over the remote server, which is work, your name, and project name. Yeah, that's a good question.
So I can create a folder there, right? Or
yes, sir. Yeah.
I can create a directory there. Okay.
Right. And I didn't mention, but the work directory is almost allow for the infinite size of, technically allowed size, but you can, terabyte size, but it'll be removed from time to time, but it can create or store the terabyte size, even terabyte size data and program.
So home, so the work is more like home in our local machine.
Right. So home directory, another thing we need to remember is that the home directory has a quota. It's a limited resource. So depending on the cluster, it'll give you 3 gigabytes or 10 gigabytes of the storage, but it'll stay permanently. So you can save some important program that you built or copied over, and then you can run that direct to that location to run the simulation. That's another way. So store the program on your home directory, running your simulation in the work directory, pointing to that software in your home directory. That's another way to run the simulation without the HPC's help.
I see.
Yeah.
And actually, the other question is on the right side after the end of the code. So when we are running the script, and the next piece of command, my understanding is that is the name of the, let's say, actually the previous slide.
Yes, sir.
So in the right side, the end of your code, you are
mhm.
making basically the script run, right?
So this is the entire contents are script, part of the script. This is the special command by the Slum software. So you utilize all the resources, the requested resources. For example, here 40 cores, and then this is the name of your software. It can be LAMP, or it can be MATLAB or Mathematica or Python. So these are
So
the
that would be, let's say if you're running Python, that would be Python.
right.
Okay.
Yeah, it is a Python. So Python 3 or something like that.
Okay.
In that case, you have to use a module load Python
Mm.
to use that. So that's a difference.
And then in the last would be our file name dot
Right.
file.
Right.
Okay.
So then you will see the result in this project folder.
Yes.
And then intermediate, the result screen output is stored in this file in the same folder. So batch out. So you'll see the screen output in this file. So then you can monitor, intermediate results by opening up these files in the middle of the calculation if you're wondering, how it works, how it runs.
So I think at the end, they will send us an email using the email address we provide that the job run is
Right.
successful, or if there is any issues with the run.
Right. So this is a particular flag that when it ends, when it fails, it sends an email to this address. You can add when it execute as well. So when you run, and you can get an email as well, because sometimes it sitting in the queue very long time. So you wanna see when it runs, then you can add another pragma options there.
So one other question. So for instance, for the nodes and the number of tasks, right? So for instance, the nodes, let's say I want to use 5 nodes, for instance. Let's assume, but 5 nodes are not available. So will that give me any kind of error, or the batch
So
will control that automatically? Like they will
yeah,
increase and will.
that's very good questions. So that's I didn't introduce the load balancing or scheduler, the what it does, but it is waiting in the queue until the resources are available. So then, if you requested too many nodes, and probably it will wait for a long time for others to finish the small jobs, but your priority get increased in the system, even if the job scheduler basically based on the first come first serve basis. But if you're longer waiting in the queue, your priority getting higher and higher, and then at the time you get the resources, you can run this. It automatically run the job and then give you results. Yeah.
So I mean that's probably I mean that problem is more inherent to any HPC system in general, but the overall performance of any task often very much dependent on the availability of the nodes, right?
Yes, sir. But I think it's a fairly large resources are available. So even if usual time, waiting time in a queue is probably 4 to 6 hours, depending on the congestion, but it's a usual time. I mean, it runs immediately for especially in the slow clusters. I introduced 3 clusters available. So Orion is fastest. Many people try to use this Orion first. So, busiest, fastest, but Scout and Shadow are always available. So if you submit a job, usually run as soon as you submit it. So if you don't care about too much about the computational time, I recommend use one of these clusters. It even without the project number, it runs within a decent amount of time, waiting time. So that's very useful.
I think that's all the questions I had. And again, I really appreciate for your time. And I think the explanations was actually very clear. And thank you for doing that.
Thank you for inviting me. I enjoyed talking with you.
Christian, if you could see if any other questions from any of the other students.
Yeah, at this time we open up questions to everyone. But if we have no more questions, we can end it here, I guess.
Sorry, Christian, I have one more question.
Oh,
Sorry.
yeah, go ahead.
Thank you for the great presentation. I really enjoyed your detailed information how to use the Slurm scripts like this. I have one question about, for example, if you want to create an environment like the TensorFlow in the machine learning application, in this slide I can see. So I want to say that a specific configuration of any environment does not affect the Slurm script, right? Or it may affect it. For example, if I want to create a TensorFlow environment as a secondary environment in Python languages. So in that area, is that any problem? Does that affect any problem for running nodes or the CPU configurations?
Right. That's a very good question. So I think that's a new problem where when we started using the Python a lot in different problems, especially the machine learning code. So the HPC side, they decided to have a minimal configurations for the TensorFlow and PyTorch as the available resources, software resources, and then users can install the additional packages in their local directory. In that way, you can run some additional packages, but that will increase your local drive size. So I'm kind of communicating with them to have a better approach now. There, in the meantime, in the near future, we'll see. Maybe we can use a Conda environment in the work directory, which is unlimited resources. Then you can create your own environment and run some calculation. If that makes sense.
Yeah, I see. So you mean we have this authority to create an environment using Conda in the local drive, right? There is no
Right.
limitation of this.
Right. If you know the pip command, PIP, so you can install the package in your local directory using -- user. So it does not store in their system directory, but your local directory. And then they are working on to give Conda environment in the work directory itself, so that you can create single folder packing everything that you need.
Okay, I see.
Install by yourself.
Yeah, I see. So this was my major question. I mean, it means that in local drive, in my work directory, I'm able to create a virtual environment using Conda to install anything like the TensorFlow or PyTorch.
Exactly. But it's an ongoing effort. So I'm still communicating with them, how efficiently they can deal with this problem. But current setup is they just offered bare bone TensorFlow software, and then you need to install those in your local directory, which consume your the allowance, you know, the
Okay, thank you.
disk allowance.
Thank you very much.
Thank you.
Is there any other questions for Sungkwang? Well, I think that's it. Appreciate you joining us, Sungkwang, and presenting on this topic. And we are going to share this on our Informs website.
Yeah. Great. Thank you for inviting me again, and thank you for organizing this seminar, Christian and other board member and advisor. Thank you very much.
Thank you.
Thank you.
Thank you, Dr. Sungkwang. Have a great rest of the day.
You too. Thank you. Bye-bye.
Bye-bye.
Thank you.